So I couldn't resist. I went ahead and plugged in the police data into the group data sheet. Here it is here. I copied the sample statistics over. Oops, there we go. And notice the average speed and the standard deviation are pretty close to each other. The difference is in the fact that they only had 15 cars. And everything stays the same, 95% confidence, right-tailed test. But look at the test statistic. You're only half a standard deviation away with a huge p-value, which means now, with a huge p-value, that means the data that you're getting is very, very close to the null hypothesis you were expecting. So in the first one, we had a small p-value, which means it's hard to believe that the average speed of one of those cars is 30 miles an hour. But now this says it's not that hard to believe that the average speed of the cars is 30 miles an hour. What I want you to think about between now and class is how can you have almost the same sample average and the same sample standard deviation, and the only thing different is the sample size, and generate such a huge difference in the test statistic and the p-value. And we'll start by talking about that on Tuesday. Just wanted to leave that with you now. Okay, so let's move onward. You now have seen pretty much any kind of test where you have a known value, like for this one, 30 miles an hour. If you're interested to try another one, you can look at this one up here to see if you've got any IQ deviation from normal with acute head trauma. So there's a known number of 100 is the average IQ of human beings according to the way IQ scores are kept. So you now have a tool where you have an average you can compare to. But what if you don't? For example, scroll down to the data sheet to here. Now I asked you all in class how many of you have ever been blasted by a commercial. Like you're watching television and the commercials come on and they just seem like they're louder. They're louder than they should be. And what I've got here is I've got some old data, because I used to think the exact same thing. I thought the exact same thing. So what I had some old data from, this is when before, now I haven't watched television in years, pretty much ever since we've had a kid. But years ago when we had normal cable television, or actually, excuse me, not cable television, just antenna television, there were commercials on after shows. And I was able to collect some data, peak decibel data. So what I did was I took each show and then I measured the commercial immediately after it for a number of shows, and this is going back at least 10 years, and I have no idea if my sampling methodology was sound, but that's okay. It's not a research methods question, it's a how do we deal with this data question. So if you look at some of these, the show was at 73 decibels and the commercial was at 75. And the show was 72 and the commercial was 75. The show was 73, the commercial was 74. And you might be thinking to yourself, well, what's the big deal? It's 1 decibel. But you have to realize that decibels are actually powers of 10. That's why they're called decibels. So, you've got 73 to 74 is actually 10 times the sound pressure or the sound intensity. So, that's a jump. That's a sizable exponential jump. Sometimes you can see that they went down, 71 to 69. Sometimes they stayed the same, 72 to 72, and so forth and so on. But what's the overriding pattern in this sample, assuming it's random? Are they going up? Are they going down? Are we unsure? Well, it is kind of hard to see. It's kind of hard to see is that's going up. This one's going up. This one's going up. That one's staying the same. This one's going down. This one's going up, down, up, same, up. Okay, I'm hearing a lot of ups. There's a down, there's an up, staying the same. So it's a little hard to know if they're going up or if they're going down or if they're staying the same on average, especially with a small sample with high volatility. I suggest if people are worried that commercials are too loud, we simply test that hypothesis and see if the data bears it out. So we'll get to that in a second. Let's go back to our templates. Okay, the template's still filled in from the cars one. So what I'll do is I'll delete some of these and we'll fill them in as we go. Okay, so we're definitely, oops, I shouldn't have deleted up here though. We're definitely still testing mu. We're testing mu up here. Okay, and the thing about it is what is mu? What is mu? It seems like we have 2 data sets here. We've got a measure of commercials loudness, and then we also have the measures of the show's loudness that precedes them. And it seems like we should have two mu's, a mu for the shows and a mu for the commercial. But the thing about it is, you have to think about that. It's not really two averages. It's really the average jump between the commercial and the show, or the show and the commercial, depending on how you want to look at it. We're not viewing the show and the commercial in isolation. What got our attention was that we're watching the show, the commercial comes on, and we're jolted. It's not that the commercial itself was loud, it's that the commercial was very different from the show itself, if there is such a difference. So let's look back at the data again. I want to look back at this data. We actually don't want to test 73 and 75, I don't think. I think we want to test this as a difference of 2. And we don't want to test this as 73, 74. I think we want to test that as a difference of 1. So here's what I propose we do. I propose we copy this into a blank Excel sheet. We'll go to our Excel stat, and I'm just gonna create a new sheet at the end here. Okay, so a blank sheet. I'm going to paste the data in, and I think what we should do personally is, if I can shrink it down so it fits better. I thought you could do it all at once. Oh well, I guess you can. Anyway, there it is. I propose we click in this cell right here and do commercial minus show, and then look at this data, because that's what we were doing kind of conversationally before. Let's make it larger so we can see it, maybe center it so it looks a little bit more obvious. I think this is what we want to look at. We want to look at the average differences between the commercial and the show. Now, some might say, well, that ignores the fact that they're 70 or they're 60 or whatever. And I'm like, yeah, that's true. That is very true. But these numbers represent the decibel difference, which is what we want to test. We don't actually want to test how loud the show is and separately how loud the commercial is. We want to test exactly sequentially how loud they are. So my claim is this is our data right here. This is our data. Positive numbers represent a larger sound intensity from the commercials than the shows. Negative numbers mean they went down, and zeros mean they stayed the same. So I think this is what we want to be looking at. So this is why it still is a single mean. If you consult your flow chart, when you're looking at your testing, which one, mu, how many, it's still 1, including matched pairs. This is what we call a matched pair test, because you actually have what appears to be at first 2 different sets of data. But it really isn't 2 different sets of data. It's really 1 set of data. You're looking at the difference between 2 measurements that are linked in some way. I'm not saying that the other kind it doesn't exist, where you actually do have 2 separate pieces of data. We're going to look at that next week together. That's when you have a control group and an experimental group, and that's very important in research. But the thing about this is there is really no control group. Well, I guess you can view the show as the control and the commercial as the effect, but this is starting with a baseline and measuring off the baseline. You're actually just looking for the distance away from baseline you went. So I believe this is the data we want to be looking at. So now let's think about it. If this is the data we want to be looking at, which well, we've taken the difference of the 2. So back to the template. Define the variable. The variable is going to be the difference in decibels between the show and commercial. Now I want to stop real quick and spell commercial, right? And give one quick mathematical / English warning here. Since it's a difference, that means you're subtracting, and subtraction is not commutative. I wrote difference in decibels between the show and the commercial. What I technically did was I did the difference between the commercial and the show. If I did the show and the commercial, technically speaking, all of these numbers would be negatives of what they are. That would be -2, -1, -3. So you just have to keep track in your mind what difference you're actually looking at. So the difference, I'm actually doing commercial minus show, but I'm going to write it as show and commercial because conversationally I think that makes more sense. Now, as far as a difference, if we do indeed believe that the commercials are louder than the shows, see if you follow me on this one, I think we want to test to see if there's a significant difference from 0. 0 would mean they're the same, right? 0 means they're the same. Anything significantly greater than 0 shows that they're not the same. I believe we're testing versus 0, and that solves the problem of we don't have a number. We actually do have a number, don't we? We've got a very important number, 0. We're going to test to see if 0 itself is exceeded by these numbers with statistical significance. Okay? So that's going to be our number we're going to test against in the Excel calculator, and we'll get to that in a second. Let's look at the errors, okay? Basing off of our car analogy from before, type 1 error is a false positive. That's claiming, you know what? I want to save the font. Claiming the commercials are louder when they aren't. False positive, right? And a false negative, claiming they aren't when they are. Claiming the commercials aren't louder, whoops, no zero there, when they are. And I'll let you decide which one of those you like better or don't like least. and you can go from there. Okay. We are definitely going to use a t distribution. And now comes the crunching part, 7 and 8, and then the decision about what we're going to do down here. And we'll see what we have to do about this. So it's still a t distribution. Okay, and make it bigger, make it jump out at you. Test statistic and p-value. We have to crunch some numbers, right? We first, knowing that we have to get an average, a standard deviation, and a sample size, I believe we need to take this data and convert it into those things. So I'm going to copy it over to my 243 sheets, and I'm going to go for stats raw data. Let's make this bigger so you can actually see the thing. I'm going to go for stats raw data. Let's paste it in here. Did it all fit? It fit beautifully. Look at that. Let's delete all this other stuff. It fit absolutely perfectly. I wish I could say I intended that. I sure didn't. Is it all there? Let me check it real quick. Yeah, I'll be there. I honestly didn't think it would fit. I thought I'd have to do some finagling. Anyway, it's got an average difference of 0.39. That's good. That's positive. If we believe the commercials are louder, it should be positive. Yay. It's got a pretty wide standard deviation, though, almost 2 decibels. We got a sample size of 23. In other words, we got a lot of noise. We got a lot of noise, not decibel noise, but statistical noise. So a small sample, relatively, with a fairly convincing average, but a fairly large standard deviation. So let's copy that over to our t-test sheet and see what that tells us. Okay, now let's just check to make sure. We need let's see, we got a correct tail selected. Whoops. There we go. We got our right tail selected. Oh, sorry, I forgot one thing, and I often do this. I apologize. We have to change our null hypothesis to 0. I often forget to do that. I should probably make a note pointing to that. Yeah, so we got to change our null hypothesis to match our data, which is going to be 0. Okay, it's a right-tailed test because we're trying to see if it exceeds the threshold for 0. And if you look at this, you see a lot of area. Scrolling down here, you can see just how much area, 14%. 1.08 test statistic. Let's put that into the template and then discuss it. Test statistics 1.8. The p-value, about 14%, which if you think about it a different way is bigger than 5%, right? Bigger than 5%. Should we reject the null hypothesis with a bigger than 5% p-value? No. Not at 95% confidence. That's a fail to reject the null hypothesis, which means it does not appear that the commercials are louder, or lorder if you're British. It does not appear. This p-value is too big. Big p-values, to say it again, a big p-value means the data you got agrees with the null hypothesis you were assuming. Your null hypothesis was that, no, the commercials are fine. They're the same as the shows, if not, if maybe even less. A large p-value agrees with that. A large p-value means, yeah, we were starting with the null, we're ending up with the null. So we don't reject it, we actually believe it, and it does not appear the commercials are louder. Now, what's interesting about this, when I collected this data, I was like, how can that actually be? How can that actually be? So what I did was, I did a little bit of digging. I think I have the PowerPoint on your resource page. Let me crack this thing open and talk to you about it. I did a little digging back in the day, and it was interesting to me, very interesting to me. As I dug, I realized that the government actually took this on a few years ago. Back in 2012, the government created a rule, the FCC, division of the government, I guess, created a rule that commercials cannot be louder than the TV shows. Okay, but we just proved statistically significantly, at least with my sample, if it's okay, was that they're not. So I did more digging. And as I discovered, the FCC actually has a website, which was great. They have a wonderfully unbiased question that says, have you ever been blasted by an excessively loud TV commercial in the last 6 months? Yes, make it stop. No, the law seems to be working. That's a wonderful, wonderful, wonderful voting mechanism, yes? Self-selected sample with crap questions. Here's your responses. And the FCC is going to feel pretty good about this because they got a 19-to-1 odds somebody's going to say, yes, make it stop. Anyway, I kept digging, and once again I found more and more data talking about this law. The clever commission is called the Commercial Advertisement Loudness Mitigation Act, CALM. Anyway, kept digging, and what I discovered was, as I dug more, the FCC actually, the rule says that commercials cannot have a larger average volume. Now the problem is, I wasn't testing average volume. I was testing peak volume. So the problem with testing peak volume is, so I'm going to get a little musical technical on you here. When you have sound waves, there's this thing you have called compression. So studios use this all the time when musicians are playing or vocalists are singing. Sometimes their voices don't get loud enough for a signal to be audible. So what they do is they compress the signal and bring up the low intensities so that they're more audible. They do the same thing with commercials. Now this says shout and whisper. I pulled this from a British website. But the shout would represent the commercial sound intensity waves, and the whisper, or the normal blue, this blue curve here, represents the TV show's waves. Notice they don't have much of a difference in maximum volume, but the average volume actually is higher. And that's what compression does. It allows you to amplify certain sounds but not past a point so they get distorted. So as I dug and read more about the FCC's rules, their rule actually deals with the average volume, not the peak volume. So my data is kind of antiquated in that it's testing the wrong thing. It's testing peak volume. I should go back and test average volume, which requires me to, well, find time to do so, which I will do one of these days. But it was it's an idea of a matched pair hypothesis test. They're great. We'll do one in class on Tuesday that involves stopwatches and a claim that one of my colleagues had to deal with back in the day. And we'll also deal with discovering if we think the human energy field exists. I got some fun stuff planned for us to do the next day we hang out together. So I hope these videos were a good jump start for us, and we'll talk more on Tuesday. Have a great weekend, friends.